Okay, so this is the next video in the embedded system video lectures. Now, in the previous video, we discussed about the core of the embedded system, and uh, the core can be fallen into any one of the four categories. And we discussed about the microprocessor as well as the microcontroller. Now we will discuss about the digital signal process. Okay, now digital signal processing. So this is the processor which is used for processing the digital signals, like the powerful specific purpose 8-bit or 16-bit or 32-bit controllers or processors can be designed to meet the computational demands. So the digital signal processors are 2 to 3 times faster than the general purpose microprocessors in the signal processing applications. Okay, so the digital signal processors implement algorithms in hardware which speeds up the execution, whereas the general purpose processors implement the algorithm in firmware, and the speed of execution depends primarily on the clock. So that is the main difference here. Okay, so the execution speed will be faster in the DSP when compared with the general purpose processor. So DSP can be viewed as a microchip which can be designed to perform high speed computational operations for addition, subtraction, multiplication, as well as division. Okay, so any digital signal processor incorporates the four key units. First one is the program memory, second one is the data memory, and third one is the computational engine, which is going to process the data, and finally the IO unit is the input and output unit, which acquires the data and from the external unit, and the processed output will be sent to the external world through the output unit. So the audio, video signal processing, telecommunication, and multimedia applications are the typical examples where the digital signal processors are employed or used. Now, we will discuss about the two different types of processor architectures. First one is the RISC and second one is the CISC. RISC stands for Reduced Instruction Set Computer and CISC stands for Complex Instruction Set Computer. Okay, so reduced instruction set, the name indicates itself that there are lesser number of instructions which are supported by the processor. So here the greater number of instructions. Okay, so the instruction pipelining and increased execution speed is there in the RISC, and generally no instruction pipeline in future. Okay, so the RISC is having the orthogonal instruction set. So that means it allows each instruction to operate on any register and it can use any addressing mode. Addressing mode is nothing but the different ways that the CPU can access the operands for the execution of an instruction. And here it is the non-orthogonal instruction set. So all instructions are not allowed to operate on any register and use any addressing mode. It is instruction specific. So the operations are performed on registers only here. The operations are performed on registers as well as memory depending upon the type of instruction. So there are large number of registers available in the RISC. Here there are the limited number of registers available here. So a programmer needs to write more code to execute a task. Here the instructions we use here less number of instructions to write a specific application because it is a CIC, complex instruction set. Here single fixed instruction, fixed length instruction. So that means let the length of the instruction you can say depending upon its size, whether it can be an 8-bit instruction or 16-bit instruction or 32-bit instruction. So here there are fixed length instructions in RISC. Here the variable length instructions. So here it is less silicon usage and pin cutout. Here it is more silicon usage. In the case of CISC, complex instruction set computer. Now we will discuss about the Harvard versus the Von Neumann architecture. Okay, so these are the two different processor architectures. Okay, so there are two memories here. First one is the program memory and second one is the data memory. Program memory is the memory where the instructions are stored and data memory is the memory where the operands are stored. So here we can use the Harvard or Von Neumann architecture for any processor or controller. The point here is whether we can use a single bus between the processor and memory, and we can use the two different buses. Okay, so that means the microprocessor controllers which are based on the Von Neumann architecture shares a single common bus for fetching both instructions and data. Here, the program memory and data memory is available only in a single chip. Whereas in the case of Von Neumann architecture, so that's why we require a single common bus for fetching both instructions and data. Program instruction, data instruction are stored in a common memory, and that we already discussed. So if it is a Harvard architecture, it will have a separate bus and instruction bus. So that means there are two separate buses, one for program memory and one for data. So that means there is a bus between CPU and the program memory, and there is a bus between CPU and the data memory. So with the Harvard architecture, the data memory can be read and written while the program memory is being accessed. So that means the CPU can simultaneously access both program and data memories in the case of Harvard architecture. In the case of Van Neumann architecture, so the CPU is having only a single shared bus. So that means at a time it can access either program memory or data memory, either instructions or data. But here in the case of Harvard architecture, the CPU can access both instructions as well as data simultaneously by using the two different buses. Okay. Thank you for listening this video.